Hey, welcome back. Good to see you again. Thanks for joining the channel. Hope you're all well. Today on the bench I have a Kenwood basic M1 power amplifier. This one's got some party tricks, and I picked it up a while ago. It's been sitting here for a number of years because I picked it up and it's not the best shape, but I bought it because it was interesting, and I love power amplifiers. But yeah, let's take that off. It's pretty beat up. It's got some battle scars, and it's probably got a history behind it that we don't know about. This is a Kenwood power amp. It's very sparse for controls. It's got 2 speaker switches, like a chunk power switch, and a headphone output. It's got a lamp here too. I suppose it's just a power lamp. It's got something that's called Sigma drive, and it has this here called dynamic linear drive. I don't know what that means, but condition wise it's kind of beat up. It's missing some black here, and this is all scratched, and if we roll it around we start to see why. It's a little bit special. It has input left and right, ground. This is our system B for speakers. This is our system A. Now it has extra speaker connectors because these are our outputs and these are our inputs. So what do you mean inputs? Well, this is your Sigma sensor. So what they're doing is they have a secondary set of lines running out to your speaker to attach to your speaker, and what they're doing is they're sensing the signal at your speaker instead of the signal at your amplifier. So they're accounting for signal loss in your speaker cables. And from that, they can get a better air correction in the amplifier. I think that's the theory behind it. Don't know any specs on this at the moment. Let's pull the lid off and have a look inside. So what's so special about this amplifier that we're interested in learning? So here's the Hi-Fi Engine listing for this amplifier. It's got a basic description. I don't know where these write-ups come from. I think they come from a manufacturer, I'm not sure, and so you just copy and paste them in here. But let's read through this. Description: unprecedented dynamic headroom, vanishing distortion, and precision control of speaker cone extrusion. These are some of the rewards that a new technology found to be found in the basic M1. A startlingly simple design concept translates into a much sought after goal of higher power handling ability combined with low distortion and outstanding tonal quality. A patented Kenwood technology, the DLD power circuit brings together the best features of a top quality medium power amplifier and a high power amplifier, totally sidetracking their disadvantages. Thus, you can get the enormous power needed to amplify the most dynamic music signal peaks. I'll skip this this paragraph here. Looks like more fluff, but this one here: highly reactive speaker loads and crest value music signals that exceeded the rated output are taken fully into stride by the basic M1. This amplifier can comfortably handle the highest dynamic peaks, even at rated listening levels. It can operate fully with speaker impedances that fall as low as 2 ohms. This amplifier is designed for frequency response accurate to within plus or minus 3 dB from 1 Hz to 300 kHz, ensuring that all signals falling within this audible range are reproduced perfectly. So, some bold claims. How does it do it? Let's look at the schematic. Alright, it all starts at the power coming in, and we have power switch, fuse, power transformer. Now this is not any ordinary power transformer. It has a black center tap, but it has 2 sets of windings. Lower voltage winding and a higher voltage winding. These windings are fed into 2 bridge rectifiers. D1, which is the higher voltage winding, so this goes D1. We have 7500 microfarad at 71 volt capacitors on both positive and negative rails, and we should get a positive negative 70 volt supply. On the lower voltage we have D3, D4, D5, D6 rectifying and supplying that rectified DC to capacitors C7, C6, 6800 microfarad at 42 volts, and this applies a plus and minus 36 volt supply. D2 is a sub-supply just for this LED on the front panel, So it have a little power supply consisting of D2 and C5 to filter it, and R2 to drop the current for this LED. Now bear with me, I'm going to try and go through this without butchering it too bad. We have two sets of output transistors. We have a low power. Where is it? Low power? Right here. Low power, Q5, Q7. And they are fed from the plus minus 36 volt supply. So that's our what they call medium power, but they call it here on the schematic low power. And it shares the emitter resistor R113 with the high power. So here's Q1 and Q3. These are high power transistors, and they are fed from the positive and negative 69 volts rails. And they also use the emitter resistor R113. So essentially we have two amplifiers stacked on top of each other. They both use the same emitter resistor. This is our speaker output line going through the relay here, and then out to the back. This is where it gets confusing for me anyway. They have a switch here and here, and then this is another switch here and here. These are time constant transistors, and these are comparators. So what they're doing is they're taking the signal that comes in this solid line, and it normally goes through to the low power amplifier, or the switch turns on and this one turns off, I believe, and then the signal can actually flow through to the high power amplifier. I don't think you'd have both amplifiers on at the same time. That's why they have this switch arrangement. Time constant, I'm not sure. Comparator, it's probably comparing a level of some kind. It's got all these diodes and stuff, so this is where it's confusing for me. I don't understand how all this works. And this output amplifier arrangement is all fed with these two drivers. There's Q21, Q25, and they're wired in series, so they provide higher gain, I'm assuming. Emitter followers, and this is where all our voltage amplification is going to happen here in these four transistors. Q61 and Q19 current mirror, and this is our bias transistor. This is a biasing diode, D29. But before we go too far, let's look at this, our input section. We have three sets of differential pairs, long tail pairs. We got differential 1, differential 2, differential 3. Our signal comes in, goes through a 4.7 microfarad cap into differential 1, and that signal flows through to differential 2. That signal flows through to differential 3. And then it goes through the biasing circuit and then the voltage amplification circuit. Let's go back to the speaker outputs. This is our speaker outputs here. We have speaker system A and speaker system B. The speaker system A has the ability to connect sensor wires. These sensor wires run from this terminal or this terminal out to the speaker and connect to the speaker, back of the speaker connections. So what you're doing is these sensors are sensing the voltage at the speaker, not at the output of the amplifier. And if we look here, this is our output of the power amplifier, our positive here and negative here. All of our negatives are tied together. It looks like all of the negatives are tied together, and they are going back to the star ground at the power supply. Our left channel comes in on this line, our right channel comes in on this line and goes through the speaker switch. This is kind of a unique speaker switch, and then it turns on either speaker A or speaker B. I think you can run them both together, I'm not sure. You should be able to. With speaker A turned on, our signal is going to flow through to our speaker terminal, and our sensor is going to flow back from the speaker, and it's going to flow through the switch, and it's going to go to sensor left or sensor right. Okay. Now here at the speaker terminal board, they have a resistor. It's a 470 ohm resistor between our output of our amplifier and the input of the sensor. And now I think they put this resistor in here just to make sure that there is a signal coming back, because I think if it's open, it might cause instability. Now, speaker system B does not have the sensors. It is running If we run through speaker B, oh, that's headphone. If I go through here, and we turn on speaker B, then we're getting speaker B, but we're getting no sensor feedback. So our Sigma sensor only works on speaker system A. Sensor left and sensor right comes back into the amplifier, goes through this 33 ohm resistor and 220 nanofarad capacitor to ground. I think what they're trying to do is just get rid of any RF interference or anything. I think this capacitor will shunt it to ground just to get rid of that. So sensor A line comes along the top here, comes back in, and it comes through this 5.K resistor, and then it's fed back into differential 1. This is our negative feedback on differential 1. And a 200 ohm resistor, there is a 1000 microfarad, 6.3 volts. This is just to shunt any AC to ground. This ground line here at the bottom is ground. This line here, coming from this side, this is our amplifier negative feedback through a 56K resistor, through the 200 ohm into the long tail pair. Alright, there it is. So I probably missed a few points, but it's pretty complicated. There's three input section has three long tail pairs. It's taking feedback from the speakers, feeding it back to the beginning of the amplifier, a low power amplifier for most music, and then on higher peaks it's switching into high power transistors. There's a lot of stuff going on here. It has a protect circuit, and that uses a basic IC chip. IC1 is a UPC 1237H, which is a very common chip. So there's a lot of stuff going on in here. Screws are out. Let's pull the lid and have a look. It's very nice. It's quite the amplifier. I don't see anything wrong with it, and I believe when I bought it, it was fully functioning, working. So I shouldn't have any issues with the amplifier itself. I'm guessing these are Elna caps. They should all be fine, but we'll test some of these. They might be failing. We don't know. Just speaker switches. Everything looks good. So I think I want to connect it up to some power, and we'll put a load on it and we'll see how it does. 6 amp fuse, looks intact. Power supply board. I don't expect to find much wrong with it other than cracked joints maybe. I don't know, I don't even think the caps would be bad in this thing, so let's just give it a test. Alright, ready to power this thing up for the first time. Here's my watt meter. Relay clicked. 17 watts. It's pretty low for an amplifier of this caliber. It's going to probably climb up. It's already at 18.5. It's going to warm up. So let's turn up the signal a bit. Now what's going on here? I got speakers turned on. No, I don't. Speakers 2. Okay, there's our signal. That's our signal. Let's keep going. Okay, I don't know how far this goes. Oh, there's our clipping. Ooh, a nasty little spike there. It's just as soon as it goes into clipping. You can even see it here a little bit. That's not cool. Alright, so that's 3.2 volts going in. Let's see. I'm going to go right there as our peak. And we're at 32.28 volts RMS. Let's turn this down. It's actually working pretty good. Let's turn this down. Okay. Alright. Next I want to have a look at this. I think this is our 1000 hertz square wave. Let's go down in frequency. Hertz. That looks beautiful for 100 hertz. Let's continue going down. 50, 40. Still looking pretty good. 30, 20, 10. It's a 10 hertz square wave. And we're just under 1 watt. Looking pretty good. Let's do the top end. Okay. 1000 hertz tone. 10 kilohertz. 9 kilohertz, sorry. 10. 20 kilohertz. I'm starting to lose it right about here, which is 67 kilohertz. This amplifier is pretty impressive. I like it. Yeah, I'm liking this amp. Doesn't look like we need to do any repairs. It is functioning as it should. But what I would like to do is pull the bottom cover off and look for cracked solders on this board and make sure that it's 100% before we put our stamp on it. Okay, just as I expected, I am seeing some cracks here. If I look hard enough, I find them. I don't think anybody's been in here before, judging from the dust, the original dust. And I think some of these solder joints need to be touched up. There's quite a few of them actually that are cracked, around the transistors mainly. So I'm going to go through and make sure this is 100%. I'll have to clean this board to make sure. Cleaning it helps me see the cracks because, for example, this one here, it's got rosin flux around the joints and you can't really tell. So I'll clean this well and then give it a good inspection, and then I'll do some spot checks on some caps. One thing I sometimes like to do if the speaker connectors in the back are caked with dust and they don't really look good, especially when they're like filthy. If I'm going to pass this amplifier along to somebody, I want these sparkling. It makes a big difference to aesthetics if these look good. So what I usually do is just desolder them and throw them in the ultrasonic cleaner, because there's no way to really clean these and get in all the nooks and crannies. So I just get in here with a soldering iron. It's pretty easy. You just got to remove 4, 8, 12 connections and then pop them out, put them in the ultrasonic, and that'll give me a chance to clean this board up for solder connections as well, because I think these ones are all good. So I did resolder the main board, and I probably made it sound worse than what it was. There was some dodgy connections with a little ring around the pad. They were not broken yet, but starting to. And then I pulled out the power supply board and did the same. This one was good, but I resoldered all the capacitors and bridge rectifiers just as a precaution, and cleaned the backs of the boards. And then I'll do the same for this. I'm going to start removing this. And like I said, it doesn't take me long. I can just go through and the only problem is there's a lot of copper back here, so you got to heat it up well. And once I get that off, I'll clean that up. But there's really not much to do to this amp. It's pretty good condition. I don't think it's seen a lot of hours. Pretty low use. Not a lot of baking on the board in the heat zones, not that I can see. So it was well cared for. Don't know if you can see the difference between the two. I think it makes a huge improvement when you clean these and you don't see all that crap on the back, dust and grime. So I'll just put these back in. Alright, I pulled the speaker relay out. It's an Omron. I don't know if you can see that. It's G2Z-222P-US. It's a 24 volt relay. It has 2 sets of contacts, one on each side and a coil in the middle. Now, this is probably easy to replace. Let's have a look at the contact resistance. This is one side. Yeah, not very good. Way over 1 ohm. Yeah, it's not good. Let's try the other side. I'll probably just end up cleaning this one. Well, that's much better. 0.5 ohm. Still not good enough though. It should be about 100 times less than that. So probably what I'll do is I'll open this thing up and clean it. Alright, those contacts are quite black with tarnish, and so I cleaned them with some 2000 grit paper, and this is what it looks like now. Got about 15 milliohms, 15, yeah. The other channel is the same, pretty much. I can show you. Quickly hook this up. Let's see here. This one's a little better, 13, 12. Yeah, that relay is going to go back in. So I've been away from the bench for about a week doing other things, and I've been thinking about this thing while I was working on other stuff. I think I just might go ahead and replace the caps in this. Not that they're bad or anything. They are showing weaknesses. Like I'm pulling out some out, and they are showing a lot weaker than a new cap of similar size and voltage. So I think I just might go through. There's not very many caps in here. There's like 25 or 27 caps, excluding the power caps. I might pull those out as well and test them while I'm here. They'll probably end up going back in because you can't see them. They're right here. They'll probably end up going back in, so they're probably fine for now. But I think I might just go ahead and do that. There's not that much for capacitors in this thing. And a lot of them are bipolars, which kind of concerns me. So I think I might just go ahead and do that. I've been doing the bias adjustment, and I have this thing on. It's been on for about half an hour or 20 minutes or so. We've got 11.5 millivolts on the left channel. The right channel is 14.5. Now it says in the manual, it says between 8 to 20 millivolts. That's quite a wide range. I don't know why they have such a wide range. It's unusual. Usually they have one value and then whatever. But we do have to do a power amplifier check. After completing power amplifier repairs, be sure to confirm the waveforms are present as indicated below. Power of the amplifier operation is not normal if these waveforms cannot be observed. So I'm trying to decipher their instructions. They don't make any sense to me because they tell you to connect leads of your oscilloscope on different pins of different boards, but they're not clear on what pin and what board. And we're supposed to be able to see this waveform as we increase power. This would be the low power amplifier, and then this would be the high power amplifier. This is to represent the switching between the two. But yeah, I think this is really confusing. And they're trying to do it in such a way that you have your oscilloscope connected to one of the B plus lines, the negative lead of it anyway. So you have to have an isolated oscilloscope. You have to be careful because you could blow this whole thing up. I couldn't figure this out. I tried reading it, I tried looking at schematics, and I couldn't figure it out. Basically what it's telling you to do is connect the positive lead of the oscilloscope to pin 15 of the power supply board, and connect the negative lead of the oscilloscope to pin 13 of the main board. Now if I look on the schematic, that's the same wire. So are they having me connect the oscilloscope across both ends of the wire and measuring the voltage drop across the wire? I don't know. It's not very clear. But not is all lost, because there is another way. They also have a flowchart method that you can use a multimeter, and you take measurements across transistors and you go through the flowchart and confirm if it's working or not. So I'm going to do it this way. It seems to be a little easier, more or less confusing. Well, that's it for this one. I'm going to wrap this one up and finish this one off. I wish it was in a little better physical condition, but this is a nice amplifier. It's got some nice design to it, and I think this Sigma drive is a good idea. You're actually sensing the signal at your speakers instead of what's coming out of the amplifier. Negative feedback typically is picked right off at the emitter resistor, but in this case they have terminals in the back. You can take it from your speaker, feed it in, and that's your negative feedback, and it eliminates a lot of distortion and error in your speaker cables, the relay, the switches. Yeah, I like this idea. I'm going to try this out and see how it sounds. A lot of good reviews about this amplifier too, so I want to try it and experience this. So alright, thanks for watching. Take care, and talk to you in the next one.